Hey everyone, welcome back. Hope you guys had an awesome spring break. Uh, so yesterday we did the assignment for electric fields. That's kind of it for electric fields. Just so you know, the assessment I'll take in will be the assignment. All those little quizzes we do are mostly just for you and for me to see how we're doing. The assignment is what is the grade I'll kind of take, and we'll move on from there. As far as tests and stuff, I'll communicate about that in the future. I'm still not exactly sure what's expected from the province, so don't worry about that now. Let's just keep learning and having fun. Of course, this is tons of fun. Okay, so we're moving to magnetic fields, and which means we're talking about magnets. Magnets are super cool. We see them all the time. They're on your fridge, they're on your phone, and the biggest one, which we're all encountering right now, no matter where you are, is the Earth. The Earth is a giant magnet. Okay, and we see them, we observe them, we know that opposites attract and similar magnet sides repel each other. But why? What makes a magnet a magnet? So that's what we're going to be talking about, and it's really interesting. And there's this really cool connection between magnets and electricity, and that's just fascinating. And so we're going to get to that kind of stuff soon. But we're going to start here with magnets. And so, why does a compass point north? It's because there's a magnet up there, right? There's this giant magnet up this mountain that's at the North Pole that's attracting our compasses. Except that's what people used to think in the early 1600s. But then Sir William Gilbert determined it's not that there's a giant magnetic mountain, it's that the whole Earth is actually a giant magnet. All right, and so that's what we're talking about. Magnets point north, or sorry, compasses point north because the Earth is a giant magnet. It actually is a magnet, and it's awesome that it is. Magnetic field. You're going to see the unit Tesla. Okay, Tesla is a guy who used magnetism to create electricity, and so they named magnetic field units after him. Okay, these can be sensed using a compass. That's how we sense where there is magnetic fields and what direction it's going. And a compass is designed to always point towards the south pole of a magnet. Okay? It always points towards the south pole of a magnet. So that's important. So if we draw lines, if this is a magnet, then you can look a magnet at this point, a compass at right here would point towards the south pole. Which means if you put a compass near a north pole of a magnet, it's going to point away from the north pole. Okay? And so what do these lines represent? These lines represent the direction a compass would point. Okay? And so here's the look that a magnet's going to have, and basically all magnets are going to look like this. It's called a bar magnet. The lines are always going to go away from the north pole and towards the south pole. And so the other thing that we see is it would go away and towards the south like that, and we can draw that on the top and the bottom. So anytime you're drawing these field lines, they should be going away from the north and towards the south, and of course they would bend. So you see some similarities to electric field lines, but this is how it kind of looks. Okay, so they point away from the north towards the south, and that's always how it looks. And inside the bar magnet is something different happening. Maybe we'll do this in purple. Inside, they're pointing like this, from the south to the north, but that's inside. Okay, and on the outside, they're always going from the north to the south. Okay, and so make sure you're reading the notes. I'm not going to go over it in detail. I'm kind of showing you how to draw these diagrams, and like I said, this is very similar to electric field diagrams. What this represents is if we would put a compass here, it would point that way. Okay, if we put a compass right here, it would point that way. And so these lines just represent the direction that a compass would point if it was placed near a bar magnet. So if we were at school, what I would have is we would have compasses, and we'd be moving them around bar magnets, and we would just observe this, but you'll just get the notes. If you have a compass at home and a magnet, then do this, and you can see that it's pretty simple. Okay, with magnets, it is simple. Opposite poles attract. And so, what does this attraction look like with these lines? Remember, lines always go away from north. We'll use in red. Away from north towards the south. Okay? And so we would see this attractive force. And so, the field lines, the compass is always going to point like this now. Okay? It's always away from the north towards the south. Okay? And instead of wrapping around here it might wrap around, but here it still might go towards the south. And this north, this will look very similar to how it would have, because there's no south to go to. It's always away from the north and towards the south. And here, it might go tight there, and towards the south. Okay, so if these two magnets right here, if these two magnets are interacting, this is what it's kind of going to look like. How will it look different when we got south on south? Remember, this is where it looks very similar to electric field lines, where we see this, the compass is going to be confused. It's not going to know which one it's more attracted to, right? So it's all in proximity. The closer you get to one, you're more attracted to that one. And so then north, away from north towards south. Away from north towards south, so these two sides should be fairly identical. Okay, and so we can draw field lines. So hopefully you're seeing some similarities. The goal is, what direction would a compass point at any place near a magnet? Once again, on the inside, it's always going towards the north. It's opposite on the inside. And we'll talk more about that later. Okay, that's discussed right here. What makes a magnet magnetic is the domain theory. Ferromagnets, okay, are made of domains, which means inside the material there's these domains that all kind of have directions, and if they're all lined up, then they're magnetic. Magnetic material means they can be lined up. And so if you break a magnet in half, if it was magnetic and all the domains were pointed one way, so these are domains. Hey Joshua, I'm recording something right now. That was my son Joshua. So if they're all pointed one way, that means it's magnetic one way. Okay, so you could draw lines in each of these. They're all pointed that way. Okay, you broke it in half, but what you notice is what changed? Not much. It's still a magnet, okay? And so what we see here is this is magnetic. If it's pointed on the inside, that means this is the north side, this is the south side. Okay, because it's always on the outside going towards the south, which means this is the south side, this is the north side. So once again, it's like this. These are two attractive magnets now, right? And we'd see this. So this looks very similar to when we had two bar magnets side to side, right? And so if you break it in half, you just have two magnets now. Here's one magnet. Here's another magnet. Two magnets. You break it in half, you got two. You put two magnets together, now you've got one magnet. This is just one big magnet now. So if we draw the field lines here, it's away from the north towards the south. And they go around and around, etc. And so if you combine two magnets, they just become one magnet. It is stronger, but it's just one. If we think of the Earth, what is the Earth? Right? We know that. What direction do compasses point? They point towards the north. right? So they're pointing towards there. They're pointing away from the south and towards the north, right? And there's even magnetic fields way up there. It stretches there, and which means if we think of it, we compare it to this magnet here, it points us towards the south. What? So this is the south, this is the north. Magnetic, right? Because our compasses, what we do is we charge them as a north, right? And so the north charged needle will point towards the south. So this is a weird thing where this is magnetic north, right? But it's because when we charge a magnet and let it float, it will point towards the South Pole, or the Earth, which is the North Pole, of course. It's very confusing. But technically this would be the south, but our north magnets point towards the north. Very bizarre. Our compasses point north. Okay. This is just some extra kind of fun stuff. Magnetic declination. Read this, and you're going to see that our North Pole is moving every single year, and that is pretty cool. So there's geographic north, and there's the magnetic north, and they're constantly moving, and so we got to take that into consideration. This is cool. Magnetic inclination. This is the fact that there's a magnetic field is three-dimensional. Okay, and so if we look back up here, okay, right at this point, if we put a compass here, it's nice and flat, right? But vertically, if we put a compass here, all of a sudden it's dipping down a bit, right? And so you can tell where on the Earth you are by a three-dimensional compass, which this is talking about, a dipping needle. And when we get directly at the North Pole, right here, we would see that the magnetic field is straight down. And that's significant, especially when we start talking about the Northern Lights. So this is where I'm going to send you to watch a video. The video is really cool about what makes Northern Lights actually happen. It all has to do with the Earth's magnetic field. Okay, so that's it for today. Tomorrow is going to be a practice lesson on this, and then we're going to move on to magnetic induction the next day. So read these notes, try to get a general understanding. These magnetic declination and magnetic inclination are two kind of bonus things. Don't get too hung up, but do read them. But there won't be a lot of testing on these two concepts. They're just kind of interesting facts that is good to know about. If you're learning about magnets, you should understand these things that they are out there. Okay, so enjoy the video. That's next, and make sure you fill in all the notes, and then tomorrow we'll get some practice with this stuff.